All right, so section 6.4 talks about the sampling distribution of a sample proportion. So last week we talked about section 6.3, a sample count. Now we're talking about a sample proportion. Okay, so again, we're going to talk about proportion problems in this section, and then the next two sections are about mean problems. So again, understand that the difference: counts, proportions, and means. Okay, so sampling distribution of the sample proportion p hat. So again, this is our symbol. So it describes the distribution of values taken by the sample proportion p hat in all possible samples of the same size from the same population. And again, when we interpret the standard deviation, we will use this phrasing as well. Now, this is a interesting little graph here. So this would be a dot plot, all right? However, instead of using dots, what they're using are p hat symbols. And again, this is essentially what we're doing. We're finding sample proportion values and plotting them on a dot plot. All right, so you got to think of every dot as a p hat value. And again, this would be the sample proportion of pennies from the year 2000s, and our sample size is 20. So again, this is an activity we would have done had we been in class, but I have a big jar of pennies. You're supposed to pick out 20, and you're supposed to count how many are from the year 2000 or above, and then out of the total, and you get your proportion that way. Okay, so again, sample proportions. This would be a sampling distribution. So when we do this, again, we need our normal distribution. We have to have a mean and standard deviation. So here's your notation for the mean of the sampling distribution for p hat and the standard deviation for the sampling distribution of p hat. So again, suppose that p hat is the proportion of successes in a simple random sample of size n drawn from a larger population with proportion of success p. Then the mean of the sampling distribution, the mean, mu sub p hat, is actually going to be the population value p. They will give you the population value, the proportion of success. We will use that value. The standard deviation of the sampling distribution of p hat is going to be this formula right here. Okay, so it's the square root of p times 1 minus p all over n. All right, so again, keep those formulas in mind. So a couple things to keep in mind about the mean and standard deviation of your sampling distribution of the sample proportion p hat. Again, I know it's a lot of words. So p hat is an unbiased estimator. That means that the mean of its sampling distribution is equal to the population value. And that's exactly what we said on the last slide. The mean of the sampling distribution for p hat is equal to the population value p. Right? That's our center. The standard deviation describes the typical distance between p hat and p. Again, remember, every dot is a p hat, and then the mean is going to be your p. So standard deviation is how far your data varies from the mean. So how far is your p hats from your p? The sampling distribution of p hat is less variable for larger samples. We talked about this, right? We want n to be large. And then the independence is required. Again, however, we can ignore it if sample size is less than 10% of the population size. That is that same idea from last section. Now, that idea ties in, I think, to the next slide. And what I'm trying to do here is talk about your sampling distribution for a sample count, which was section 6.3, which was the last video, versus your sample proportion in section 6.4. Notice that these two distributions are exactly the same. However, one is talking about the number of pennies out of 20, because our sample size is 20, versus one is talking about the proportion. So let's look at this value right here, right? That would be a value of 7. So our x was equal to 7. That means out of 20 pennies, we had 7 be in the year 2000s. This penny right here is at a proportion of 0.35. That number comes from, that's a p hat value, that number comes from taking your 7 that you had and dividing by 20. When you do that, you get 0.35. So the only difference between the sample count and the sample proportion is that you're dividing by the total. That's the only difference. So the formula for standard deviation is a variation of the formula of the standard deviation from section 6.3, that whole square root thing. So be aware of that, okay? Essentially the same thing. All right, so let's do our first example here. It says, what proportion of students have a smartphone? Suppose that 43% of students at a large high school own a smartphone. As part of a school-wide technology study, the principal surveys an SRS of n equals 100 students. Let p hat be the proportion of students in the sample who own a smartphone. Part A, calculate the mean and standard deviation of the sampling distribution for p hat. Well, in the problem, this 43% is your population proportion. That's your p-value, right? So your p-value is 0.43. And then the sample size n is 100. These are the two key numbers we need to calculate the mean and standard deviation. So to calculate the mean of our sampling distribution p hat, we need to just write down p because that's what it's equal to, 0.43. Remember, proportions have no units, so that's it. They're just a percentage written as a decimal. And then to find the standard deviation for the sampling distribution of p hat, we have to use this formula, right? It's all inside a square root. So we take p times 1 minus p, and we divide it by the sample size, and that all is inside one big square root. So I'm going to take the time to show you how we're going to do that in Desmos Graphing Calculator. Okay. Okay, so let's go to Desmos Graphing Calculator. Let me clear what I'm working on here. Okay, so the first thing I would do is I would find that square root. So again, remember it's here, square root. And then I would press the fraction bar right away. So there's my two pieces, right? So now we're going to type in 0.43, parenthesis 1 minus 0.43, close parenthesis. That's the top. Hit the arrow button down, and here goes your 100 inside. And typically we'll go 3 or 4 decimals. So because there's a 0 here, I'm actually going to go, I think, to 4 decimals this case. So 1, 2, 3. I'm going to go to that 5, and I'm going to leave it. So 0. So our standard deviation is 0.0495. So again, use your best judgment whether you go 3 or 4 decimals, depending on the rounding. Like I wouldn't go to 3 decimals because then I have to round this 5. This makes the 9 become a 10. That's too difficult rounding. Okay, so 3 or 4 decimals is good. Again, let me just show you real fast. Make sure you know the difference between here. So this would be not right. So again, I hope you can see the difference is in the first one, the fraction is inside the square root. In this one, the fraction cuts the square root off from the bottom. That's wrong. The n has to be inside the square root. Okay, so be aware of that difference. Okay, so now let's talk about interpreting the standard deviations. How are we going to interpret it? Well, it's going to start off very much like we did last time. We're going to use that definition of a sampling distribution to talk about all possible samples. So who is taking these samples? It's the principal. So we're going to say if the principal, remember he's a principal, right? Principal's your pal, took all possible samples, list the sample size of size 100, and then list the population. So the population is this large high school. From this large high school, and now we say the sample proportion. So now we're doing the actual interpreting of the standard deviation. The sample proportion of students, and now I'm just doing it right here. The sample proportion, or you could say the proportion of students in the sample, but I just put sample proportion. The sample proportion of students who own a smartphone. And now here's the whole standard deviation. It typically varies. I would say would typically vary by, and now you list your standard deviation, 0.0495. There are no units because it's a proportion from the, and now instead of saying mean, we're always in when we're talking about sampling distributions of sample proportions, it's how it varies from the actual true proportion, from the true proportion of 0.43. And there we go. Okay. All right, so that's objective one. Objective two is coming.